As we finish simple harmonic motion, I want to do a review of the formulas involved and how they're related to each other. So with all the formulas we've seen in this topic can be broken down into two categories. So the first of those would be the kinematics of simple harmonic motion. And then the velocity and the acceleration. Now we saw that these versions of the formulas we can easily arrive at by looking at graphs of the motion. For these, we arrived at those through using calculus. And since we may or may not know calculus, if we don't know calculus, we can just remember that this V0, the V max, is equal to x naught omega, and that the maximum acceleration is equal to x naught omega squared. When we get to dynamics, it's a simple matter of starting with our definition of momentum and substituting in for velocity. And when it comes to F net equals ma, Newton's second law, it's a simple matter of substituting in for the acceleration. When we get to kinetic energy of a block, say moving, or any object that's undergoing simple harmonic motion, we have our general definition of kinetic energy. And then it's a matter of substituting in for V. And when it comes to the potential energy of a spring system, this is our potential energy of a spring, well, delta x is x. It's a matter of substituting in for x. And I almost want to have a reminder here for everyone that the total energy of a system, as we define with the law of conservation of energy, is the sum of all the energies, and that was just changing back and forth from each other. And so we can define the system based on the different types of energies involved. Some may be lost to thermal energy. There could be gravitational potential energy or kinetic energy and elastic potential energy of the spring, or any combination of two or three of them depending on the situation, but that the total remains constant. Getting at the unique things to simple harmonic motion, we have first our definition of simple harmonic motion, that the acceleration is opposite and proportional to the displacement. And it also is the case that k is equal to omega squared, which we derived in a previous installment. Omega itself is defined as the rate of completion of the cycle, or 2 pi radians, the entire cycle, over the time it takes to complete the cycle, or the rate of completion of the cycle, the angular frequency, the angular velocity. It could also be defined as 2 pi f, since period is 1 over frequency and frequency is 1 over the period. And we also derive these two expressions for the period of a spring and the period of a pendulum. So these are all of the equations that we might want to use. And if we, in simple harmonic motion, and we would just remember that V0 is x naught omega, and the maximum acceleration is x naught omega squared. So those are things to remember. So there are a lot of formulas there. Most of them are just simply applying the kinematics equations and substituting those into the formulas in dynamics, momentum, and energy. There are some unique ones that relate to definitions. Definition, definition, definition. And this is a relation derived from some that are worth being familiar with. Now over here on the right, I've included all of those that are on this page. These are the only ones that are on the AP formula sheet. So we would recognize this one as that. This as this line of equations. Again, not very useful, not as useful, not written in the form of definitions. And these are just straightforward. Everything else is missing. So that's a recap of the formulas we might want to know or use in the field of simple harmonic motion.